So your actually the differential equation is d2x by dt2 plus 2 gamma dx by dt plus omega square x equals to 0. Not 0. So it is ft divided by n. So this is your spring mass dashboard system. You can call it a real oscillator or ideal or similar stuff like that. So now case 3 we will consider it's a forced free damped oscillation. So in case 3 we will take force free damped oscillation. That means you don't have any external force. That means Ft equals to 0 and it's a damped oscillator, so gamma is not equal to 0. So your differential equation is d2x dt2 2 gamma dx by dt plus omega square x equals to 0. So this is your differential equation for force free damped oscillation. So not yesterday. So in the last class, maybe we had told you that how can you play the Mr. PK. Okay, now it's okay. So now, so what is the process of solving this equation? So I told you have to take a trial solution. If you take a trial solution, that is actually x equal to जो मैंने last time में लिया the same trial solution. So we know that in case of trial solution, we have to put similar stuff e to the power mt. Now if you put this trial solution here, so you will get a characteristic equation which is actually m square plus 2 gamma m plus omega square equals to 0. So now solution is actually last class में हम लोग किए थे, which is actually क्या था ये minus gamma plus minus root over of gamma square minus omega square. So this is your solution of this characteristic equation. So now your n1 equals to minus gamma plus root over of gamma square minus omega square, and m2 equals to minus gamma root over of minus gamma square minus omega square. So now we have to consider different cases. Now if we see this term, if gamma is greater than omega, then there is no problem. It is a real quantity. Okay. But if gamma is less than omega, so it will become imaginary quantity. The m1 or m2 will become imaginary. So that will give you different physical situation. So now again we will take some cases. Case 1, where we can consider that gamma is less than omega. The complicated case. That means what is gamma? Gamma is what? Gamma is actually your damping coefficient.
Yes, sir, b by 2m.
Yeah, so damping coefficient is very less than omega. That means it's a under damped. मतलब the damping force जो है, it is not affecting the natural oscillation in a large extent. So that means we can call it under damped condition. Okay, so this is we can call under damped condition. So if we put value of gamma, you will get the real so 2b by n, b by n equals less than gamma 2b by n, b by n. So b by
d by m.
So b is less than 2 a omega. So this is the condition for under damped condition. So now if I put this condition here, then your M1 will become imaginary. So what I have to do? Take minus omega. If you take minus here, so that means you have to keep the parameter inside the cert positive. Otherwise, you will get again you will get a imaginary coordinate. So let's take minus common. So if I take minus common here, so you can write this one m for plus minus I इसको आप लिख सकते हैं root over of omega square minus gamma square, because now omega square minus gamma square is positive. Okay, so now there is no problem. So now you can write your m1 equals to sorry m equal to minus gamma plus minus इसको आप लिख सकते हैं, let's say this is alpha I alpha. Okay, so that means omega square minus gamma square root over this one equal to, let's say it is alpha, just to make it very simple. So now we have two solutions of m1, they are imaginary solution. So this is your two solution of the characteristics equation, they are imaginary, obviously imaginary. Now m1 is minus gamma plus I alpha and m2 equals to minus gamma minus I alpha. So these are the two solutions. So now from the differential equation, so if you see, so if you know that m1 and m2 are the two roots of characteristics equation, then general solution you can write y equals to c1 e to the power m1x plus c2 e to the power m2x. Just you write this, that will give you your it's x, it's a general solution. Now in this case, so if I put the value of m1 here, m2 here, you will get the solution. Okay, so I will just put it here. So if I put it here, so that means your solution will be, so xt will be, देखिए e to the power minus gamma is in the both the solution you have. So now what you can take e to the power minus, so that means let me write down. So e to the power m1t plus c2 e to the power m2t. So now if we put the value, so now m1 means what? Minus gamma. m2 is also there minus gamma. So now you can take minus gamma common out. Obviously minus gamma t is there. So that will give you. So inside में क्या रहेगा आपका? So it will give you c1 e to the power I alpha plus c2 e to the power minus I alpha. Okay, so that is what you will get. So now again we will do the same thing to get our actual recognizable solution. So that means, so this should be real. So in that case, this is real. So these are imaginary. So that means C1 and C2 must be imaginary. And C1 is complex conjugate of C2. These two you have to apply here to get a real solution. It's a mathematical, not say lemma or conjecture, you can say it, you can prove it. So in that case, now
it is above C2.
Yes.
Sir, what superscript is written above C2?
What can you repeat it?
So C1 is equal to C2 superscript. I didn't see. It is not. I can watch clearly.
So this is not C1 equal to C2. This is C1 is actually C2 whole to the power star. That means C1 is complex conjugate of C2. And C1 C2 must be imaginary. देखिए देखिए ये रियल है, आपका सॉल्यूशन रियल है, टोटल सॉल्यूशन. This part is real, these two part is imaginary. So now if I say C1 C2 is real, then xt cannot be imaginary, cannot be real at all. ये कैलेंडर कैसे आ गया? अरे कोई प्रेजेंट कर रहा है क्या? If anyone is presenting, please take out yourself. Okay, now, okay. So this is what we have learned in the last treatment also. So now again, what we will do? We will take C1, the complex form of C1, complex form of C1 equal to एक imaginary quantity को we always express in polar form. So r e to the power I theta. In similar way, we can write this is I phi or I whatever I theta whatever. Okay. So let's say I theta or I phi whatever I theta, because otherwise it will confuse with the earlier one. So again, then C2 will be complex conjugate of C1, so that means it will become C e to the power minus I theta. Okay. So this is two things which is coming from these two implication. Okay. So now what we do, we put the value of here. So that means your xt will become e to the power minus gamma t. What is the value of C1? So C will come out again because in the both the term we have C. Also alpha t is there. This term. So now if we put here the value of C1 and C2 here, so gamma t will come out and sorry, C will come out. Then it will become e to the power alpha t minus theta. Plus, so in this case, C2, it will become e to the power minus, if you take common, so I is there again. Okay. I, so it is alpha t plus theta. So in the previous thing, we did the same thing also. If we divided by 2 and multiplied by 2, then this term is nothing but cos alpha t plus theta. So xt equal to 2c e to the power minus gamma t cos alpha t plus theta. So this is the solution. So now you can do the another thing. Now if we multiply divided by 2i suppose and multiply by 2i, same thing you can also do. So in that case your solution will become xt equal to, ये क्या हो जाएगा आपका फिर? It will become 2i e to the power minus gamma t. C तो था आपका 2ic and it will become cos, क्या होगा आपका sin alpha t plus theta. So these are the two solutions. So now this is just a representation. So if you want to take a real solution, then you have to take the real part of this solution. That means you have to just write here the real part of this solution will give you, and this is the this is also, it's a real quantity, so you don't have to write real again. So now this is the solution. So now if we have a under damped condition, so your solution will be something like that. So let us examine what is the nature of the solution. Who is sending WhatsApp? Okay. So is it okay? So now, so your solution is now xt. Let's say this is the, now you can see this is the amplitude. and this is your phase of oscillation. Okay? So now in simple harmonic motion, that means free oscillation, whatever oscillation. So we know that the solution was something like that, omega t plus phi. Okay. So now here you have alpha t plus phi. So what is alpha? You can put it here without any hesitation. So now we put, let's say this is something A. Now it is not a constant, it's a function of time. Okay. So cos, what is alpha? Alpha हम लोगों ने क्या लिया था?
Frequency.
Omega square minus x square. So cos, cos तो लिया है. Omega square minus gamma square t plus theta. That's all. So now see, so now it's almost similar. See, we have a omega t plus phi. So we have alpha t plus phi. So this is your alpha. So alpha is a constant. Omega is also constant. Okay. So now if you see in this case A is constant. So that means if I plot the oscillation for simple harmonic motion, so this is x. So this is t and this is xt. If you plot it, so this is the oscillation amplitude is fixed. That means A और इसके बीच में ये swing करेगा. Okay, so this is the implication of simple harmonic motion. But in this case, see, A is not a constant. A is actually where AT equals to 2C e to the power minus gamma t. So this is your A. So that means the amplitude is not straight line like this. Okay, here it will see. Oh, I forgot to record it. Okay. So now, if you see, A is not a constant, so it is actually proportional to e to the power minus gamma t. So now, do you know how the functional graph of e to the power x looks like? So e to the power x, if you plot e to the power x, so x e to the power minus ax, if you plot it, so it will be, so now if you say that x equal to 0, so it will be 1. Okay, e to the power 0 is 1, and now if I put e to the power minus infinity, so it will become 0. So something like that. So now, so it will look like this. This is actually proportional to e to the power minus ax. So now, what is the A? A is the coefficient of the decrease. If A is larger, you have a faster decrease. If your A is smaller, you have a smaller decrease. But these two things is okay. So now if I apply this part, so that means A will become, so now at A t equal to 0, what will happen? T equal to 0, it will become 1, it will become 2C. Okay, so let's say 2C equals to A. So that means maybe A0 e to the power minus gamma t. So now at t equal to 0, so it will become 2C, which is A0. Okay, and then it will go, if you go up to infinity, then your AT will become 0. So now instead of having this graph, you will get something like this. The envelope of, so let's say this is your T and this is your XT. Okay. So now, so as I said that if we put T equal to 0, so that means T equal to 0 means, so it will become at t equal to 0, AT will become A0. At t equal to infinity, AT will become 0. Okay. So now this is your A0 and this is your minus a0. So we know that actually your e to the power function will like this. So if you go infinity, so it will be perfectly symmetric in the other side also. Okay. So now in between that, so now if I take t equal to 0, then cos theta will become 1. So that means it will become a0. So in between a0 and minus a0, it will swing like this. So if you go infinite time, then the oscillation will die out. So that means it is a simple harmonic oscillation. That means the in overdamped condition, the oscillation is a simple harmonic oscillation SHM or जो भी है और free oscillation. Oscillation is a free oscillation with decreasing amplitude. Okay, so this is the second implication of this calculation of cases if you have a under damped condition, and it will die out. You cannot mathematically say that after some time it will become almost zero. So it will continue to infinite time, but the oscillation, suppose that t equal to 0, you will have a very big oscillation. Like जब आप झोले में झूलते हैं, at first you will see very big amplitude of oscillation, and धीरे धीरे वो oscillation चलता रहेगा, but the amplitude, the extent of oscillation वो कमते infinite time में zero हो जाएगा. So this is what we can get in case of under damped condition. Okay, so now we will take the second. ये ठीक है? Is there any question?
Yes, sir.
No, sir.
क्या क्वेश्चन है? हेलो, कोई क्वेश्चन है?
No, sir.
Oh, very good. आज छापते हैं ना? 10 बजे क्लास. Okay, now let us take the second case, case B. In case B, we will consider that gamma is greater than omega. So that means we call it overdamping condition. So in the case B, let's say gamma is greater than omega. So that means we can call it overdamped condition. Overdamped condition. Overdamped condition means the damping will dominate. So that means B by Q is greater than equal to omega. So that means B is greater than 2A omega. So this is the physical condition for overdamped oscillation. So now again it's very easy. So your A is, we know that is plus minus क्या था ये minus gamma plus minus root over of gamma square minus omega square. So this is your A. So now, so again we can consider so n1 beta square equal to gamma square. So this is a positive quantity. That means gamma square minus omega square is greater than 0. So there is no point, so there is no problem of keeping this one as it is. So now, so if we put this value here, So A will become minus gamma plus minus क्या होगा ये beta. So now if it is so that means your two solution will be M1 equal to minus gamma plus beta, that is beta minus gamma, or M2 equal to beta minus beta minus gamma. So these are the two solutions. So now again we will do the same thing. Your the solution xt is c1 e to the power m1 t plus c2 e to the power m2 t. So now if I put the value here, क्या होगा ये simply आपका now you can take it. So it's a real quantity. So it's no problem. You can take another quantity for that. So if you take this one mu, then this one will become क्या होगा ये? We take this one as a mu, and this one will become maybe minus. Let's say you cannot represent by one entity. Let's say this is a mu2. Okay, right. So in this case, it will become e to the power mu1 t plus c2 e to the power mu2 t. So now this is what? This is actually you can also write down in a other way around. So let's take this one as a minus mu. If I do that, my question is something. If you have a damped motion, then this has to be minus. Okay. So now because e to the power x is an increasing function. So if we plot e to the power x, it will be increasing function. But if we plot e to the power minus x, so it will be decreasing function. So that means the function you are describing here, so it should be negative. So that means let's put this one as minus mu1. Minus mu1 means what? Minus mu1 means actually mu equal to, so that means mu equal to gamma minus beta, mu1 equal to. And in similar way, if I put this one minus mu2, so that means mu2 equal to क्या होगा आपका? Beta plus gamma. Okay.
Beta plus gamma. But why, sir, you have put there minus in there?
No. So what we know for damping, the amplitude should decrease. Suppose if you are damping, amplitude should decrease. That means what I'm trying to say, if you plot, suppose if I make it plus, then what will happen? So now if I put e to the power x, a is plus, okay, with x, how it will look like? It will look like, so let's say this is your a, it will become like this. It's an increasing function.
Yes, sir.
So if I put plus here, so that means because of damping, your amplitude of oscillation will keep on increasing. It will not be a good representation for that. So that's why we are making this one negative. So that means depending on that, so it should be negative here. Otherwise, you cannot explain that damping will decrease the motion. Okay. So now, what I'm trying to say, so similarly, so depending on the value of mu1 and mu2, so now mu2 can be positive, does not matter. So because of depending on the value of suppose this one, beta and gamma, so this will be always positive. But here you have a difference, so there's a chance that mu1 could be negative or positive. Okay, because there is a difference. So it's a positive quantity. So now that means suppose if I take one extreme case, okay, so like that. So it is not the general case. So that means this is a wave one, oscillation one, and this is your oscillation 2. So now, what is if I want to express the oscillation one? Let's say this is t, and I'm saying that this is your x1 t, and this is your x2 t. Okay. So now if I plot x1 t, so what will happen? So it will be like this, because it's a decreasing function. So this is your c1, and after infinite time it will become 0. So again, for second one, so let's say this is c2. So this will become, the oscillation 2 will become something like that. Okay, I'm taking the extreme cases, they are opposite. That means this is positive, this is negative, or this is negative, or this is positive. Okay, but they are all decreasing function. They are contributing out of phase here. देखिए ये इसका नेगेटिव एम्पलीट्यूड मैक्सिमम है, और ये घटते 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 के जीरो की तरफ जा रहा है, ये इसका पॉजिटिव एम्पलीट्यूड मैक्सिमम है. ये ऑलवेज सेम नहीं है, डिपेंडिंग ऑन द वैल्यू ऑफ beta and gamma, or better to say mu1 and mu2, the graph will be different. But I am taking one extreme case where the c1 c2 is contributing out of phase together in the oscillation. It's a general case. I am taking one simple special case where these two oscillations x1 t and let's say this is your x2 t are contributing to the oscillation, because these are two separate oscillations. Okay, these two oscillations superimpose each other to give you the total oscillation. So now, if I plot this one, see, let's say this is, it could be like this, So if this is your resultant oscillation, like that. So now, what I'm trying to say that it's a generalized curve. Okay, so that means if I plot this one, so this is xt. It's not it's xt obviously, which is actually x1t plus x2t. So this is your resultant curve. So that means, see, you will have a kind of simple harmonic oscillation with a small, how to say, with a small portion of simple harmonic motion with a decreasing amplitude. After that, it will become flat and die out very quickly. Okay, so that means it's a very damped. It's so damped that it will not complete one single oscillation at all. So that's why it's called over damped condition. So that means it is damped. So this is the resultant oscillation. You can call it. This is the resultant oscillation. Okay, so if we see the resultant oscillation, then see it is just trying to complete one single simple harmonic oscillation. After that, but it could not. After that, it's become flat and dies out very quickly. So that means what? Suppose if you have a shock absorber in your bike, okay. So now you got forced oscillation because of the uneven load. Okay, and now you have a huge damping in your springs or shock absorbing system. So that means you will just go, your seat will just go from, it will first of all it will just go up. Okay, so it will start from here, then it will just cross the normalized condition, then it will go to the negative direction, then it will become dies out. So that is what we need. Otherwise, you will just keep on swinging like that. So that is actually how to say, free oscillation with the decreasing amplitude. But this is a overdamped. The amplitude of the resultant oscillation is actually decreasing so fast that it is not completing one single oscillation at all. So that is the case B. And now critically damped is there. That means where they are exactly equal each other, and we can see what we can get. Okay. Now we can use the case C.
So here amplitude is constant most of the
Yeah.
times. Amplitude constant रहेगा ना इधर से इस ग्राफ.
नहीं एम्पलीट्यूड का कांस्टेंट है ये तो एम्पलीट्यूड का ही है दिस इज द so to what with the amplitude so suppose in the first case your regarded amplitude was like this the oscillation is like that okay so now what is the amplitude was like this okay e to the power minus omega in the last case में था ठीक है free oscillation
Sir, one example of that graph you have drawn in real life situation.
this one
Yes, sir.
this one if you
Yes,
go
sir.
your grandfather law it may not die out. It's a damped oscillation, almost very little damping is there. So a pendulum will keep on swinging over and over. And this infinite means it's not infinite time, it's compared to something. Suppose if you take what is the smallest unit of a clock, maybe 1 second. So if compared to that, if the grandfather clock pendulum is swinging one the whole day, it is infinite actually in comparison to 1 second. Okay, so this is what an example of a under-damped oscillation where you have an infinite time of oscillation, but the oscillation amplitude will decrease. So now here if I see, so this is the resultant oscillation, okay, like this. So now what is the amplitude? So this is your amplitude.
Yes, sir.
So it is critically damped. So it's up to infinity. It's not like that. It is getting zero in very fast somewhere t equal to t1. Okay, it's not like that. It's up to infinity is there to get zero. But at t equal to at a certain time, at t equal to t1, it will become zero. Okay, the oscillation will die out very fast. But if I want to make the oscillation zero in the last place, you have to go up to t equal to infinity. Otherwise, it will not be zero. Okay, this is the difference between overdamped or underdamped and overdamped. These are the all real life situations we always experience in our everyday life. Okay, now next is critically damped. Critically damped means gamma is exactly equal to the omega.
Omega, yes,
It is
sir.
so critical that it's exactly equal to the frequency of the free oscillation. Time is now time to very good. आज बहुत कम लोग ज्वाइन किया ये इसकी वजह से तो नहीं है माइक्रोसॉफ्ट टीम की वजह से तो नहीं है हेलो
लग तो रहा है
है
यस सर
तो टीम
Yes, sir.
ज्वाइन नहीं कर पा रहा है आज ऑलमोस्ट हाफ लोगों ने ज्वाइन किया
40 है सर.
हाँ otherwise we have always 50 55 or something okay that's good so now what I'm trying to say that the case C where we can use a critically damped condition that means where so omega gamma is exactly equal to omega so that means we say it's a critically damped condition critically damped वो जो ओवरडैम्प था उसी का ही एक पार्ट है जहां पे गामा विल बिकम ओमेगा okay so now there is a mathematically very interesting situation so that means b by 2n equal to omega then b is exactly equal to 2n omega okay so it's critically damped mathematically it's very interesting because an equal to minus gamma plus minus root over of gamma square minus omega square. So this part will become 0. So that means an equal to minus gamma Okay, so now the problem is, so you have a one solution, okay, of the characteristics equation instead of two. So that means we have to make it two जबरदस्ती आपको करना पड़ेगा. So in that case, this formula will not solve here. जो मैंने ये किया था x equal to yx equal to c1 into the power n1x plus c2 into the power n2x. It will not work. It's only work when n1 is not equal to n2. आप अगर क्लास 2 में याद होगा जब कैरेक्टरिस्टिक्स इक्वेशन का रूट्स they are real or imaginary does not matter. If they are unequal, then only you can use this formula. Otherwise, if m1 equal to m2 equal to m equal, in that case, if x equals to, you have to make it in a different way. That so c1 plus c2x e to the power gamma x, sorry, mx. I'm going to leave there. So this is how we have to write the solution. If these two roots are equal, if they are not equal, then you have to write in this way. Okay. So similarly, we have equal roots here. Then we have to use different format. So xt will now solution. Xt will become c1 plus c2t e to the power minus n. Now n is minus gamma, so it is t. Okay. So now we have a two-way again. One is c1 e to the power minus gamma t. Another way is c2t e to the power minus gamma t. So now, so let's say this is your x1t. And this is your, we can try to understand what it looks like, because this is different. So this is not constant. This is a function of time. Okay. So let's say this is your a. Okay. Or a is actually at. Okay. So that means now if I want to plot this one, how it will look like? So it is a, obviously, see, if you see this part, it is a exponential decay. So there will be a decay. Obviously, it does not matter, but the pattern of decay will change. So now, if I plot this one, let's say on the plot how it will look like. So if you have e to the power minus gamma t or minus gamma t, they are not sinusoidal. They are exponential decay function, obviously. So now it's very difficult to understand how these two functions, if I multiply them, it will look like. Okay. So now I don't know how to plot it until unless if we use a software, maybe Mathematica or something. So if you really want to see how the solution look like, we can try in Mathematica. Otherwise, it's just very difficult. Suppose we can plot this one. Okay, it's very easy. It's just exponential decreasing function. But if I want to plot this one, it's very difficult. So you have a function like this e to the power minus x, and now you have a function like this x. If I multiply them, how it will look like, it's very difficult to say without using any software. Okay, so now it is an exponential decreasing function, so it will look like this. Above that, I cannot say without the help of any plotting software. So if I plot this one xt, this is t, so it will be a exponential decay function. The oscillation, above that we cannot say further. Oscillation is a exponentially decaying function. That's all. इससे ज़्यादा कहना मुश्किल है without solving in a proper. So that's all for module 1. We completed the module 1. So maybe tomorrow I will solve some tutorial for that. After that, I will give you some assignment which you have to complete in the next week. Okay? आज छुट्टी कर देते हैं फिर. Do you have any question about this module, whatever we taught? Hello?
No, sir.
No, very good, very good. So you make your class notes with the help of internet, with the help of books, and then you try to understand what we have taught during this module. I am not going into the detail of this module because if you want to go detail in the module, then you have to take all the terms together. Force, damping, everything together. Then it will become very much complicated. And you will understand there are two solutions, transient solution and steady state solution. Suppose if you start a bike, okay, so initially it's very difficult to control. After some time, maybe 10 minutes or 20 minutes, the motion of the bike does not depends on how you started the bike. Okay, so that you can explain with that transient and steady state solution. If you take all the terms together, that means d2x by dt2 OB term dx by dt plus omega square x equals to जो ft by उसको आप लेंगे m0 sin omega t by m. ये अगर सब एक साथ लेंगे तो जाके थोड़ा सा एक अच्छा फील आएगा. Or it will be complicated. It will be worthy of a graduate student like you. But in JUT, we don't have that provision. So now what you have to learn as an assignment, first of all, जो मैंने बताया था, as an assignment, ये करिएगा assignment. जो मैंने पढ़ाया नहीं लेकिन बोला था बहुत इंपॉर्टेंट है, वो एग्जाम में देता ही नहीं. असाइनमेंट फर्स्ट इज पोटेंशियल एनर्जी ऑफ सिंपल हार्मोनिक मोशन. पोटेंशियल एंड काइनेटिक एनर्जी ऑफ सिंपल हार्मोनिक मोशन एंड सो टोटल एनर्जी E equal to PE plus KE is always constant. 2. Calculate the average energy of SH. These two are your assignment. So जो क्लास 2 में आप लोगों ने किए थे, just you have to recapitulate it. So that's all for today.
Sir, what is written in second?
क्या?
Second point में क्या लिखा है सर? Calculate the average.
Average energy of SHM, simple harmonic motion. और फिर also average energy.
सर पोटेंशियल एनर्जी काइनेटिक एनर्जी डिराइव करना है पहले, फिर
डिराइव करना है, फिर ये दोनों कांस्टेंट है दिखाना है.
ओके सर.
देन एवरेज ये जो टोटल एनर्जी निकल गया, इफ यू टेक द एवरेज ऑफ फॉर अ फुल साइकिल from 0 to t time period, it is how much is the value. Okay, that's all for today. I have another class. So shall we leave it?